Every second, billions of devices track their physical locations with incredible precision. We have all grown accustomed to digital maps that guide a car through a complex intersection or track a cargo ship across empty oceans. We often imagine this works like a two-way conversation, that satellites are actively watching us from above, tracking our movements in real time. But satellites do not know where you are. They do not receive any signals from your phone, and they have no way of knowing you even exist. GPS functions like a network of lighthouses. A lighthouse does not search for ships. It simply broadcasts a continuous beam. It is up to the captain to observe that light and calculate their own position. GPS satellites do exactly the same thing, broadcasting a constant, one-way radio whisper to anyone listening. This raises a difficult question. If no one is tracking you from space, how does a one-way signal allow your phone to calculate its location within a few meters? The process begins 20,000 kilometers above Earth. A network of roughly 31 active satellites orbits the planet at 14,000 kilometers per hour. Each of these satellites carries a secret payload, an atomic clock. These instruments are so stable they lose only 1 second every few 100,000 years. Every satellite uses this precision to broadcast just 2 pieces of data: its current position in space and the exact time the message was sent. Positioning begins with a conversion, turning units of time into a physical measurement of space. Radio waves travel at the speed of light, nearly 300,000 kilometers per second. When your phone receives a signal, it notes the time of arrival and compares it to the timestamp of when the message was sent. By measuring that microscopic delay, your phone can determine its exact distance from the satellite. The math requires absolute perfection. As this diagram of the equation distance equals speed times time shows, an error of just 1/1,000,000th of a second results in a location error of about 300 meters on the ground. To achieve precise navigation, your phone must first master the measurement of time. One satellite only tells you how far away you are, placing you somewhere on the surface of a massive sphere. Adding a second satellite narrows your location to a circle where the 2 spheres meet. A third satellite reduces the possibilities further, leaving just 2 distinct points in space. This geometry only works if the phone and the satellite share the exact same time. But while the satellites carry multi-million-dollar atomic instruments, your phone relies on a basic quartz clock. This timing mismatch causes the distance spheres to overlap imperfectly. A fourth satellite provides the additional measurement needed to solve for this offset, effectively syncing your phone with the atomic clocks in orbit and locking the intersection onto a single point on the ground. Terrestrial obstacles can still interfere. If a radio signal bounces off a skyscraper before reaching your phone, the travel time increases. Your phone calculates a longer distance than reality, causing your location to jump. This is known as multipath error. Even without buildings in the way, the system must account for the laws of relativity. Because the satellites move so fast and orbit in weaker gravity, time itself moves at a different rate for them than it does for us on the ground. These relativistic effects cause the satellite clocks to run fast by about 38 microseconds every day. Your phone compensates for this by solving Einstein's equations in real time. Without this correction, GPS locations would drift by 10 kilometers every single day, making the entire network useless. The US GPS system is part of a larger global web. Russia operates GLONASS, Europe has Galileo, and China maintains the Beidou network. Modern smartphones often listen to all of these systems simultaneously. By combining signals from dozens of satellites, receivers can now achieve accuracy within a few centimeters. This precision allows for self-driving cars, automated precision farming, and the landing of reusable rockets. The next time you see that blue dot on your screen, remember the invisible work happening behind it. In a fraction of a second, your device is solving complex geometry and relativistic physics. GPS is a massive engineering feat that turns the fundamental laws of the universe into a tool for mapping the movement of billions of people every day.